We have moist air at 33 degrees C, 1 ATM, and 30% relative humidity, and it has a volumetric flow rate of 0.47 meters cubed per second, and it flows over a cooling coil. And it exits after the cooling coil at 15 degrees C. Determine the relative humidity at the exit. So it's like phi2, the heat transfer from the air in kilojoules per kilogram of the dry air. So you have a little inlet, outlet, there's your coil, and it's a cooling coil, so you might want to put a drip pan in case there's some condensate. It flows in at state 1, out at state 2. You do a little energy balance around that coil, and the coil, there's a heat transfer out of the air because it's the water that's flowing through the cooling coil is getting warmer. So really cold water comes into the coil, warmer water leaves the coil, but the Q dot is out of the air. You do an energy balance. Q dot out, should put a dot up there, is equal to the mass flow rate of dry air through the system times the enthalpy 1 minus enthalpy 2. So this is the mixture enthalpies accounting for the, it's for the moist air, it accounts for the moisture content. So for part B, they want it in kilojoules per kilogram of dry air. That's lowercase q, which is q dot out, divided by m dot dry air, which is just H1 minus H2. Difference in those mixture enthalpies. Part C, what is the mass flow rate of the dry air? The mass flow rate of the dry air, it'll be the volumetric flow rate. That's this right there. AV, cross-sectional area, normal velocity, is the product. You can use the AV as a volumetric flow rate, times the density, or 1 over the specific volume inlet. So it has some specific volume on the inlet. That's how you would calculate the mass flow rate of the dry air. And then the last, for part D, what is the rate of heat transfer from the air? Q dot out. Well, you would just use the answer from part C and the answer from part B to calculate M dot, or Q dot out. So let's go to the chart. Did you locate where state 1 is on the chart? Where is the dry bulb of 33 and a relative humidity of 30%? So on your chart you should find a dry bulb of, what did we say, 33? That's right here, true? So somewhere along that line at a relative humidity of 30%, looks like they intersect right at that point. So there's state 1. Now it's going to be cooled. When you cool it, you drop the dry bulb until you hit the dew point. You may not cool it enough to hit the dew point. So as you cool it, it's going to go with constant humidity ratio, lowering the dry bulb temperature until it was cooled to what temperature? Did we stop the cooling at? Did we say 15 degrees C? There's 15 degrees C. So it comes across to that point right there. It looks like you would have to cool it all the way to 13 degrees C before it would start to condense. Hence, that mixture at 33 C and 30% relative humidity has a dew point temperature of 13 degrees C. But we'll stop the cooling at 15, true? So what is the answer for part A? What is the relative humidity at the exit? This is the exit right there. What do you get off of your chart? 90? 90%. Now, you have to take the difference of two enthalpies for answer to part B. So what is the enthalpy at state 1? This is state 1 right here. What is the enthalpy at state 1? What do you get? 57 is a good number. So you'll extrapolate back up, and it's around 57 kilojoules per kilogram. How about the enthalpy at state 2? There's state 2 right there. What is that mixture enthalpy?
39.
39. So right around here, 39. So the difference is 18. So lowercase q, you're being cooled or out, is 18 kilojoules per kilogram of dry air. Now the next one, for the inlet state, we wanted the specific volume of our moist air mixture, true? At state 1. We wanted, remember, this is our equation for part C. We want that specific volume at state 1. We would then take the volumetric flow rate, divide it by specific volume, and get the mass flow rate. So, what is the specific volume at state 1? 0.88? I got a couple 0.88s. So, look, this is a line of constant specific volume of 0.85, true? This is a line of constant specific volume of 0.90, right? And so you can see this is probably 0.86, 0.87, 0.88. Sure, it looks like 0.88. So the specific volume. So the mass flow rate is the volumetric flow rate, which is 0.47 meters cubed per second times 0.88, or divided by 0.88 meters cubed per kilogram of dry air. And you have the mass flow rate of the dry air then to be 0.534 kilograms of dry air per second. Just a question. Will the mass flow rate of the moist air be greater than, equal to, or less than 0.534 kilograms per second? It'll be slightly greater than, because this 0.534 kilograms is only the dry air contribution. And the moist air is a combination of dry air and vapor. How about the last part? What is Q dot? Well, you just multiply the answer for part B times the answer for part, and you find that Q dot is equal to 9.61 kilowatts. That's the rate of cooling needing to be provided by that cooling coil. Yes, this Q dot is the lowercase q times m dot of the dry air. Let's then change up the problem ever so slightly. So now the change is that you start at 33, 1 atm, 30% relative humidity with the same volumetric flow rate. That's not changed, but you cool it until it exits at 5 degrees C. What is the relative humidity at the exit if it exits at 5 degrees C? It's below the dew point temperature, so it's going to cool until it hits 13. And as you try to go from 13 to 12, it'll have to reduce the amount of humidity because it'll hit 100% relative humidity. Some will dew out. And then you'll go down to continue to 10, then continue to cool until you get down here to 5 degrees C, and that's where it'll stop right there. So your ending point has shifted to this point down here. So this is the new point 2, the exit. So the relative humidity at this point right here, phi, is 100%. Okay, at the exit, what is the wet bulb temperature? We said its dry bulb is 5 degrees C and relative humidity 100%. What's the wet bulb temperature? 5 degrees C. What's the dew point temperature? 5 degrees C. All three of those temperatures are coincident at that line of 100% relative humidity. Okay, then what is the enthalpy? The moist air enthalpy? About 19. So it goes to 19. Okay, so let's take a look. What is the answer to part B? It's the change in the enthalpy. So Q is equal to 57 minus 19, so it's 38 kilojoules per kilogram of dry air. So it's a lot more. What was it before? 18. Now it's 38.